Hello everybody, I welcome you all to NCAS Geology class. Today I will discuss about mid-oceanic ridges. The mid-oceanic ridges form prominent relief features in the ocean floors. If you take into account the mid-oceanic ridges in the oceans, it accounts for about 1/3 of the total surface area of the oceans. So this speaks what a major relief feature is the mid-oceanic ridge in the oceans. So they extend about 65,000 kilometers of length with a width about 2,000 to 3,000 kilometers, having height 2 to 3 kilometers, so that the vertical and horizontal ratio becomes 1:5,000. And these ridges, they mostly occupy the central portion of all major oceans, and that's why the name has been given as mid-oceanic ridges. So these ridges, they form a prominent feature in the oceans, and therefore they are of great interest, for which detailed surveys have been made to explore why such ridges have developed in the mid of the oceans and what is the mechanism behind their formation. During the Second World War time, much of the ocean floor were explored, and during that time it was observed that the sea floor is found to expand on both sides of the mid-oceanic ridges. So the mid-oceanic ridges rise and push the lithospheric plate sideways, because of which the oceans appear to be expanding. And the mid-oceanic ridges have been thoroughly studied over years, since 1960s onwards, and the detailed morphology of mid-oceanic ridges have been found out. So let us discuss about these mid-oceanic ridges. What are these ridges which are found in the ocean basins, and what is the mechanism of their formation? That I will discuss in my present topic. So let us discuss in detail about these mid-oceanic ridges. The mid-oceanic ridges are the mid-Atlantic ridge, which is found in the Atlantic Ocean, East Pacific ridge, which is found in the Pacific Ocean. Similarly, in Indian Ocean, we have the Indian Ocean ridge, we have the Lomonosov ridge in the Arctic Ocean, we have the Pacific Atlantic ridge toward the south side of the Pacific Ocean. So these are the major ridges that we see in the ocean basins. And let us discuss what are their general features, or what are the general characteristics of these mid-ocean ridges. They represent new oceanic crust that develops due to upwelling of basaltic lava or magma from the asthenosphere or from the mantle, particularly at the site of the diverging plate boundaries. So mid-oceanic ridges are the features that we see to develop at the diverging lithospheric plate boundaries, where new oceanic crust is being created. And if we look at the world map, we can see these mid-oceanic ridges. So this is from this point, from Iceland, and it is extending all through the Atlantic Ocean up to this end. This is mid-Atlantic ridge, and this is East Pacific ridge in the Pacific Ocean. This is Chile ridge. This is the Pacific Atlantic ridge, and here it is the Indian Ocean ridge. It has been bifurcated into two parts, the southwestern side part and the southeastern side part. And we have the Gakkel ridge in the here. So these are the major ridges, oceanic ridges that have developed along the diverging plate boundaries. These are the diverging plate boundaries. Diverging plate boundaries. Diverging plate boundaries. So the mid-oceanic ridges are the features that are confined to the diverging plate boundaries. And if we see that the new oceanic crust which is being created at the mid-oceanic ridge, they are found to be composed of these layers. They are composed of these layers. At the base we have the periodote, followed by layered periodote, layered gabbro, and these parts are generally below the sea surface, and towards the top we find the basaltic dikes, pillow basalts and sediments which make the sea floor. So this is the general composition of the rock types which are being generated at the mid-oceanic ridges. This is the site where the mid-oceanic ridge is being created, and the two plates they are pushed on both sides. Thus, new oceanic crust is always created along the mid-oceanic ridges, and the oceanic crusts are found to, or the lithospheric plates on both sides of the ridge are found to be pushed sideways. And in this manner, these mid-ocean ridges are being created in the oceans. So the mid-ocean ridges, they are made out of the lava or magma that gets erupted along the diverging plate boundaries. The rise of this magma at the diverging plate boundary is attributed to the convection current or the convection current motion that takes place within the mantle or within the astrosphere. And this rise of magma or lava at the divergent plate boundary causes the oceanic plates to drift away from the boundary, creating a condition for accumulation of magma or lava to give rise to volcanic mountains or ridges or new oceanic crust. So they form typical submarine relief features mostly found submerged within the sea. If you look at the entire length of the mid-ocean ridges, most part of these ridges are found to be submerged within the ocean surface. And at few places they are found to project above the sea level where they are described as islands, such as Iceland, which is coming on the mid-Atlantic ridge. Mauritius, Lakshadweep, they come on the Indian Ocean ridge. So the mid-ocean ridges are mostly found to be submerged within the sea. The ridges are fairly continuous with sinuous pattern of distribution. They are centrally or laterocentrally found to occur in the oceans. And these mid-ocean ridges, they constitute the longest chain of mountains on the Earth's surface, because they account for about 65,000 kilometers. If you take into account the longest mountain chain on the continents, it will be Andes mountain chain. But if you take into account the total, or if you consider the longest chain of mountains of the Earth's surface, it will be the mid-oceanic ridges. The ridges present a central zone called the main range, which consists of several parallel ridges. They constitute the crystal province. This province shows block faulting with a central lift valley, lateral block mountains with steep scarp faces inwardly dipping into the valley. If we see any mid-ocean ridge, it is found to present a centrally sunken valley. This is a rift valley. And we find symmetrical arrangement of valleys on both sides of these mid-oceanic ridges. And as we move away from the ridge axis, these valleys, they merge with the ocean floor. So we have the ridge, and the central portion of the ridges are occupied by these rift valleys. The deep valley that exists all along the axis of the mid-ocean ridge, with width it is found to range around 15 kilometers with a depth of around 2.5 kilometers. Such a deep valley that exists in the central portion of the mid-oceanic ridges. Thus this valley bisects the ridge meridionally, that is parallel to the north-south meridian, and it has been there in case of mid-Atlantic ridge. Mostly the ridges are elongated in north-south direction, and thus these valleys are found to bisect the ridges meridionally, as we see in case of the mid-Atlantic ridge. On the flanks of the main range, we have this rift valley, and on the flanks we have a series of flats, step like with dipping inwardly, which are designated as terraced zone. These are the terraced zone. Individual terraces vary in width from about 2 to 80 kilometers, and collectively they range in width from 350 to 450 kilometers. So, from the central lift valley on both sides, the flats are found which constitute the terraced zone, and they are followed by the third zone which lies between the terraced zone and the sea floor. It represents the mountainous part that are distinct from the other two zones. So if we take into account we have the centrally sunken rift valley, then flats, then ridges, then the highlands or mountains. In this manner, the mid-ocean ridges present their structure: central lift valley surrounded by the flats, which are followed by the mountainous part that merges with the sea basins. And this type of typical structure is found in case of mid-Atlantic ridge. Besides this, the mid-ocean ridges are found to be dissected by deep fractures perpendicular to the line of the strike. These fractures become transform faults and displace the crystal province depending on the force of extrusion of magma or lava at the divergent boundary, making thus the ridges to be sinuous. Because we know that magma erupts along the mid-oceanic ridges. In this manner it erupts. It pushes these two plates sideways, and the rate of upwelling of this magma is not uniform all along the length of the plate boundary, and therefore the pushing of the plates is not uniform everywhere, as a result of which cracks develop, these cracks. And these parts may be drifted. So it becomes, the structure becomes like this. It becomes like this. That's why the structure is sinuous. It is not in a straight manner. We do not find these features because the pooling of magma is not taking place uniformly along the entire boundary of the lithospheric plates. Because of this unequal pushing, these cracks develop or the fractures develop, and these fractures later get converted into the transform faults. We have the medius ridges at Aden, the ON fracture zone at Arabian Sea links to Aden with the Indian Oceanic Ridge, and Romance fracture zone at the Mid-Atlantic Ridge. These are the fractures, long fractures. Besides this, these mid-oceanic ridges are the sites of high heat flow because the magmatic material is found to be appalling. That's why there is high heat flow, and there is, because of this lava extrusion or magma intrusion, the entire site is noted for its shallow focus earthquakes, noted for its seismicity, or that is for low focus earthquakes. And these mid-ocean ridges, they are the sites of positive gravity anomaly because new landmass is being, new oceanic crust is being created. The 2/3 of the entire lava eruption of the earth annually takes place through mid-oceanic ridges. That we have to remember. 2/3 of the entire lava eruption that takes place over the earth, that annually takes place through the mid-oceanic ridges. The basalts are found to be low in potassium and olivine. Compositionally, rocks are the mid-oceanic ridge basalts. For a ridge of about 1.6 km height, the root of the ridge is found to be around 30 kilometers, which are made up of basalts. And there are bilaterally symmetrical stripes of magnetic minerals which are aligned with the formation of new oceanic crust. If this is the ridge, on both sides we have the stripes of volcanic rocks. These are the volcanic rocks which have been pushed from the MOR. So these are the stripes of volcanic rocks, and if the magnetic field of these magnetic minerals are studied, they present magnetic normal, magnetic reverse, magnetic normal, magnetic reverse polarity depend upon the polarity existing at the time of formation of these igneous rocks, these volcanic rocks. Here we have to keep in mind that the Earth's magnetic field is found to change over time. In the present, time is having the magnetic normal period and it is the Brunhes period. And on both sides of the mid-ocean ridges we find the stripes of magnetic minerals with their polarity distinctly represented by the alignment of magnetic minerals contained in the volcanic rocks. So these stripes show magnetic normal and reverse polarity depending upon the magnetic polarity of the Earth that changes with time. The edge of the oceanic crust increases symmetrically on both directions away from the ridge axis with zero edge on the ridge crest to increase on both sides of the ridge axis. So as you move from the ridge crest, so the edge increases and it becomes more and more at the depth more and more as we go away from the ridge axis. And this has been tested from the presence of these magnetic minerals. Because the Brunn's normal that the magnetic minerals show, they range in age up to 0.7 billion years from present. 0 to 0.7 million years. This is the Brunn's normal period. Brunn's magnetic normal polarity. That now the present the Earth is facing. Time will come, this normality, this normal polarity will change, and it is related to the geodynamism that operates within the outer core of the Earth, which controls the magnetic field of the Earth. So the arrangement of these magnetic stripes on both sides of the mid-oceanic ridges, they prove that the oceanic crust is found to be older from the mid-oceanic ridges on both sides. And the oceanic crust is not found to be older than 180 million years. If we take into account the age of the ocean floors all over the globe, nowhere it is found to be greater in age more than 180 million years. That means the new oceanic crust is being created at the mid-oceanic ridges. The old oceanic crusts have been destroyed with the passage of time, because of which we do not find the old oceanic crust, and the maximum age of the oceanic crust is found to be 180 million years. And the age of the oceanic crust at the MOR is 0. At the crest of the mid-ocean ridge is varying from 0 sideways up to 180 MA. 180 million years. So, mid-oceanic ridges are the sites where new rock is being created, and it is found to be very young in age. Then a rise of the sea floor at MOR leads to eustatic changes, a rise in sea level, because the new oceanic crust is being created at the MORs. So the ocean floor is shifted with the formation of the new rocks, and so this oceanic water is shifted and it rises. So eustatic, it is involved with the eustatic rise at the sea level, and the depth of the ocean floor increases away from the ridge axis to the trench. So ocean floor is negligible at the ridge crest, and gradually from the ridge crest, so here it is, the depth is 0. Depth of the sea floor is 0, and gradually as you go away from the ridge on both sides, the depth increases. Depth of sea floor increases from ocean surface. So depth of the ocean increases from the ridge crest to the trenches, or on both sides of the ridge crest, the ocean floor is found to deepen gradually outwards. And another feature of the oceans is the magnesium-calcium ratio of the ocean floor, of the seawater near the ridges. And in case of fast spreading ridge, this ratio becomes less, becomes low at fast spreading ridge, and in slow spreading ridge it becomes high at slow spreading ridge. And if you take into the global average, on that basis, the seawater shows either high ratio or low ratio. So that has been studied. In fast spreading center at the East Pacific rise, for example, there is high supply of magma, high heat flow, intense hydrothermal circulation, strong reaction of seawater with the basalts at high temperature. And there occurs exchange of the magnesium from the seawater with the basalts, as a result of which the calcium is released from the basalts to the oceanic water, leading to Mg by C ratio to decrease less than 2. This occurs in high spreading ridges, where the spreading rate from the ridge is very high, high spreading rate. There we find this ratio to be low, and it leads to calcium rich oceanic water, as a result of which the sea becomes calcite sea, as we find in case of Jurassic period, Cretaceous period, calcite sea. Opposite happens in case of the slow spreading ridge. At slow spreading center, there is low supply of magma, less heat flow, weak hydrothermal activity, less seawater and rock interaction. Thus, there is smaller exchange of Mg with Ca, as we find in case of Paleozoic time and present time. It is producing high Mg by Ca ratio greater than 2. So in Paleozoic time and present time, we find that this ratio is high, and therefore we do not find this sea to be calcitic. Here the seawater becomes aragonitic. It becomes aragonitic. So we find the formation of aragonite sea in case of slow spreading ridges. If you take into account the global average, then this condition prevails at the present time. Aragonite sea in Mesozoic time and in present time, particularly from late Cretaceous to present. It leads to, if you take on the global average, it is slow spreading, and that's why the seas are aragonitic, as a result of which we find the formation of coral reefs. Coral reefs are being produced because of this aragonitic sea condition. So we have the fast spreading ridge, where the condition is favorable for low Mg by Ca ratio, leading to calcitic sea, and in slow spreading ridges the condition leads to high Mg by Ca ratio, and it is a condition for formation of aragonite, as is prevailing in present day oceans. Every year, through volcanic eruption, about 50 to 60 km cube of new oceanic crust is created at the mid-ocean ridges. As surface area of the earth is conserved, the same volume of oceanic crust is destroyed at the convergent boundaries. This will have to take place because this total surface area of the earth is constant. If a new crust is being created here, somewhere the crust will have to be destroyed. So new crust is created at the MOR, and that is diverging plate boundary, and the oceanic crust is being destroyed at the convergent plate boundary. So both occur together, as a result of which the total surface area of the earth is found to be conserved. The MORs show upwelling of basalts along with release of black smokers, which are caused by meeting of the magma with percolating seawater. Because the extrusion of lava takes place along with gaseous emanations. And the lava is found to contain hydrogen, chlorine, iron, manganese, sulfuric acid, helium, hydrogen sulfate, methane, carbon dioxide, hydrogen, calcium, potassium, lithium, copper, zinc. All these are there, and they react with the percolating seawater. And there occurs exchange of these ions, and we find mineral deposit along the vents occurring in mid-ocean ridges. So the black smokers, black gas, black volatiles, they result due to interaction of the percolating seawater with the magmatic emanations, and it leads to the deposition of economic minerals. And away from the vent, we find the occurrence of white smokers. So black smokers and white smokers, they are related to volcanism that takes place within the sea. In the ridges, they present steep slope, tall rugged surface at slow spreading center. For example, mid-Atlantic ridge. Mid-Atlantic ridge presenting a very rugged or uneven surface, rough surface. But at the fast spreading ridge, for example, East Pacific ridge, the topography is gentle sloping with broad swell of the sea floor having a small height. That's why it is called as a rise. It is not called a ridge. It is not very steep. It is gentle sloping. That's why it is called rise. And it is East Pacific rise in case of high spreading rate, or it is associated with high spreading rate. East Pacific rise is noted for high spreading rate. That's why it is presenting a gentle sloping surface. And in case of mid-Atlantic ridge, it is steep, ridge shaped. So what are the different causes that are responsible for the origin of the mid-ocean ridges? The causes are the ridge push. The new material is being erupted along the ridge. So the two plates, lithospheric plates, are pushed sideways, making room for accumulation of the volcanic material or the lava material to form new crust at the MOR. So pushing will be there by forceful extrusion of lava. That is ridge push. Similarly, slab pull. We know when lava extrusion is taking place, it is moving like this. This is the lithospheric plate. It is moving like this, and there will be underplating of these lavas at the base of these lithospheric plates, and this will become like this. So it will be thicker to this side because of underplating. The lava that will be erupted here, and some will be moving like this below the lithospheric plate, and in this condition it may be incorporated as a part of this lithospheric plates. So plate will become heavy, dense as we move away from the ridge axis, and because of its thickening, it becomes heavy and it pulls the plate towards the trench where the lithospheric plates, they face subduction, and finally they are found to be absorbed within the mantle, so that the new crust created is found to be balanced by the melting of the old oceanic crust at the convergent boundary. So slab pull will be there, ridge push and slab pull. Besides this, we have the dragging effect of the mantle. As the lava is moving like this below the plates, it is having its dragging effect over the plate. So plates are pushed sideways, making room for accumulation of lava and magma in this portion to form the new oceanic crust. So these are the three causes: ridge push, slab pull, and the mantle drag. Now let us discuss about the different types of the mid-ocean ridges that are found over the Earth's surface. The major ridge is the major ridge is the mid-Atlantic ridge. It occurs centrally in the Atlantic Ocean that I have shown in the map. Its length is around 16,000 kilometers. Its spreading rate is very slow type, 2 to 5 centimeters per year. Depth of the ridge is 2 to 3 kilometers from the ridge top to the ocean floor. The topography is very rugged. It forms the islands at Iceland, because at Iceland this mid-Atlantic ridge is exposed, so it forms Iceland. The hotspots are Some hotspots are located near these mid-Atlantic ridge, such as Azores, Ascension, Tristan da Cunha, Bouvet, and it forms the longest mid-ocean ridge of the world. There is lack of pelagic sediments at the ridge crest, which explains the formation of new oceanic crust there, and the ocean floor is expanding on both sides, and here the pelagic sediments are not there, and gradually as you go sideways, a very small thickness of pelagic sediments are there. That means this new oceanic crust is being created here, and the ocean floor is expanding on both sides. So we say the Atlantic Ocean is expanding. We have the East Pacific rise. It is another important mid-ocean ridge in the Pacific Ocean. It has fast spreading center. So the fast spreading center is confined to the Pacific Ocean. The rate is about 6 to 16 centimeters per year. So there is abundant supply of magma. Ridge is narrow. It is forming a rise. Topography is smooth and broad. Length is about 13,000 kilometers. Rift valley is shallow or absent. When this rift valley is prominently present in case of mid-Atlantic ridge, the islands associated with the East Pacific rise, Galapagos, which form ridge type of triple junction, and this East Pacific rise extends from the Californian Sea up to the bottom of the Australia till joining with the Indian Ocean ridge, or we can say it extends from Juan de Fuca plate through San Andreas fault, Cocos plate, Nazca plate, Chile ridge to join with the Indian Ocean ridge. This Pacific plate moves westward, whereas Nazca, Cocos and Antarctica they move eastward. So the East Pacific rise represents a fast spreading ridge, and it is providing a gentle sloping surface. That's why it is known as rise, extending from California to the extreme south. Then Indian Ocean ridge. It is a very long ridge present in Indian Ocean, parts in Arabian Sea. So it occurs at the center of the Indian Ocean. It extends over 12,000 kilometers. Spreading rate is slow, 3 to 6 centimeters per year. Elevation is 2.5 to 3 kilometers above the sea floor, divided into several segments by transform faults and fracture zones. The segments are Carlsberg Ridge. It is the northern part of the Indian Ocean ridge. It is present in the Arabian Sea between Somali plate and the Indian plate. It is the part of central Indian ridge, but it is occurring to the north. Then central Indian ridge, it extends from the Carlsberg ridge between Africa and Indo-Australian plate. Actually, the whole ridge from the Red Sea up to Rodriguez Junction is the Central Indian Ridge, and its northern part is called as Carlsbad Ridge. The Southeast Indian Ridge, it extends between Australia and Antarctica from Rodriguez Triple Junction. Then Southwest Indian Ridge, it extends between Africa and Antarctica till the meeting point with the South Atlantic Ridge. The ridges present rugged and segmented topography. Several islands are associated with the Indian Ocean Ridge, such as Reunion, Mauritius, which are present in Mauritius in Arabian Sea, Reunion in Indian Ocean. This is in Southeast Indian Ocean, Amsterdam. So these are the ridges which are found in Indian Ocean. In case of Indian Ocean ridge, the rift valleys at the central Indian ridges are narrow and present below lavas and seated dikes. The Rodriguez Triple Junction lies at the junction of Southeast Indian Ridge and Southwest Indian Ridge and the Central Indian Ridge. So it is a triple junction. Southwest Indian Ridge do not show transform faults. Then Pacific Antarctic Ridge, it connects the East Pacific Ridge with the Indian Ocean Ridge, lying between New Zealand and Antarctica. The plates involved are Pacific and Antarctica. The spreading rate is moderate, 6 to 8 centimeters per year. Length is about 5,000 kilometers. It presents broad ridge crest with active hydrothermal fields. Then Chile Ridge, it is part of the East Pacific Ridge towards the Chile from the Easter Island Triple Junction. It is southern extension of East Pacific Ridge. It lies between Nazca Plate and the Antarctica Plate. Length is about 1,000 to 1,500 kilometers. Spreading rate is 6 to 7 centimeters per year. And the total, if you take into account total length of the mid-oceanic ridge in the Pacific Antarctic region, it is around 18,000 to 20,000 kilometers. Then these are the major ridges. Besides this, we have some other ridges. Aden Ridge, which is present in the Gulf of Aden between Somalia and the Arab Peninsula. It extends from the ON fracture in the Arabian Sea to Afar Triple Junction. Or it originates from the Central Indian Ridge and it extends up to the Afar Triple Junction, Aden Ridge, between Somalia and Arab Peninsula. These two have developed because of the mantle plumes and development of this triple junction. The Explorer Ridge, it is seismologically very active. It is present in the Pacific. It shows hydrothermal vent called Magic Mountain, located 240 km west of Vancouver Island, British Columbia, Canada, at north extremity of Pacific spreading axis near Juan de Fuca, or towards the north of Juan de Fuca, this ridge is present. So this is another small ridge. Then Lomonosov Ridge, it is in Arctic Ocean. Length is about 1800 kilometers, width 60 to 200 kilometers, height is about 3 kilometers, and it is found below 1 kilometer of the sea level. It is composed of continental crust, that is granites and sedimentary rocks. So it is a continental, it is of continental origin. It is not related to the divergent plate motion. It is not of basalt decomposition. So it is of continental origin. But it is found within the sea in the Arctic Ocean. It separates Eurasian basin and Amerasian basin and stretches between Siberia, Russia and the North America that is Greenland, Canada region. So this ridge is present there. It is noted for each occurrence of oil and gas beneath the sediments. So it is not related to divergent plate motion. It is a continental crust ridge having continental origin. It is believed to be the fragment of Eurasia continent separated during the opening of Arctic Ocean 60 to 70 million years back. So this is Lomonosov Ridge, and beside this we have the Gakkel Ridge. Gakkel Ridge, explore Ridge. This is Lomonosov Ridge. Then we have the 90-degree East Ridge. So 90-degree East Ridge is present in Indian Ocean through the Bay of Bengal, having its location along 90-degree east longitude. It is a seismic ridge in Indian Ocean. It is of volcanic origin, runs north-south along 90-degree east longitude, formed by Kerguelen hotspot, which is a mantle plume. When Indian plate moved northward above the hotspot from Cretaceous to Cenozoic time, these volcanic mounds have been produced by volcanism, which and this during the 80 to 40 million years ago, this movement was taking place, and the ridge has been produced from a number of volcanic eruptions that came out from the Kerguelen hotspot, and it is not related to mid-oceanic ridge. It is a seismic ridge. Similarly, we have Walvis Ridge. It is located in the South Atlantic Ocean. It appears close to the mid-Atlantic ridge, or it appears as if it is the trail of the mid-Atlantic ridge. It is not related to mid-oceanic ridge. Its origin is related to hotspot magmatism over Tristan da Cunha hotspot, which occurred near Atlantic spreading center. It extends from Namibian coast towards Tristan da Cunha Islands. So it is a part of the African plate. Similarly, we have another ridge, that is Rio Grande Ridge, which is occurring on the west side of the Walvis Ridge. Age is Cretaceous. It is located in the southwest Atlantic Ocean near the east coast of Brazil. It is a part of South American plate, when Walvis is a part of African plate. And it is related to hotspot magmatism of Tristan da Cunha during Cretaceous period. So Walvis Ridge and Rio Grande Ridge are paired hotspot features, not spreading ridges, and they formed during Cretaceous time in South Atlantic by the Tristan da Cunha hotspot extrusion. So Rio Grande Ridge and Walvis Ridge, they are present in South Atlantic Ocean, and the 90-degree East Ridge, it is not related to mid-ocean ridge, but it is a seismic ridge which has been produced by the hotspot extrusion in the Indian Ocean. So this is all about the mid-oceanic ridges, and these ridges are very, very important in geology because they are associated with the diverging plate boundaries where new oceanic crust is being created, and at its expense, or to accommodate the formation of this new oceanic crust, there occurs subduction of the old oceanic crust at the convergent boundary zones, which we see in case of the Pacific margins. All along the Pacific margin, there are the convergent boundary zones where the Pacific plate is subducting below the Eurasian plate or Indian plate, and along the west coast of North America and South American plate, where gestation oceanic plate is taking place. So you can say that the Pacific Ocean is contracting, whereas the Atlantic Ocean is expanding because of these mid-oceanic ridges. This is all about the mid-ocean ridges that I wanted to discuss in my today's discussion. Thank you all.